All right. Okay, let's take another shot at this. Again, I'm Ken Loudermilk. I'm a senior chief engineer for Titus, and we're going to discuss psychrometrics as it relates to HVAC system processes. Psychrometrics is the science of water and air that deals with the properties of moist air mixtures. Whether you're a recent graduate or an experienced engineer, it's always good to review the basics of psychrometrics, as its understanding is key to improving HVAC system processes. The psychrometric chart is a tool we can use to identify the properties of a moist air mixture. The chart shown here is based on air mixtures at sea level or 14.7 psi barometric pressure. The chart allows you to quantify numerous properties of an air mixture by simply identifying two of its attributes. All of the other physical and thermodynamic properties of the moist air mixture may thus be determined by the use of the psychrometric chart. That's actually pretty handy for what we need to do. Let's identify a few terms that are helpful to know when analyzing a moist air mixture. The dry bulb temperature is that which is measured by a thermometer that is freely exposed to an air mixture and shielded from any radiation. The dry bulb temperature is not affected by the mixture's moisture content. Wet bulb temperature is that read by a thermometer whose bulb is covered by a water-soaked cloth over which the air mixture is blown. The adiabatic evaporation of water from the cloth transfers heat to the airstream, which renders the cloth's surface temperature lower than the dry bulb temperature of the air passing over it. Absolute humidity is the mass ratio of water vapor to dry air in a moist air mixture. It's also referred to as humidity ratio and expressed as pounds of water per pound of dry air. Relative humidity, expressed as a percentage, is the ratio of the mixture's moisture content to that of a fully saturated mixture at the same dry bulb temperature. We'll discuss this a little later in the presentation. The dew point temperature of a moist air mixture is the dry bulb temperature at which it becomes fully saturated and its water vapor begins to condense. Finally, specific volume and density relate the volume and mass of an air mixture. They're used to convert volume flow rates to mass flow rates. Now let's begin to explore the psychrometric chart itself. The x-axis of the chart represents a mixture's dry bulb temperature, which is indexed by vertical lines within the body of the chart. The y-axis represents the moisture content of the mixture, expressed as a mass ratio of its water vapor to dry air. This is referred to as the absolute humidity or humidity ratio, designated by the letter W and commonly shown in pounds of water per pound of dry air. Humidity ratio can also, though, be expressed in grains of water per pound of dry air. There are 7,000 grains per pound of water, so this results in values without multiple decimal extensions. I personally find this much easier to use, so we'll continue to use grains throughout the rest of this webinar. Finally, the wet bulb temperature is indicated by diagonal lines on the chart. Note that for a given dry bulb temperature, a reduced wet bulb indicates a lower mixture moisture content. Notice the curve formed by the left end termination of the wet bulb temperature lines. This curve is known as the saturation line. It's established by points where the mixture's dry and wet bulb temperatures are the same. The point at which a mixture's dry and wet bulb temperatures are the same is also referenced to as its dew point temperature. The dew point temperature represents the minimum temperature a mixture may be cooled to before it starts to condense moisture. Also note that any change in moisture content directly affects the dew point temperature of the mixture. The pink curves in the body of the chart represent equal values of relative humidity. The relative humidity of the moist air mixture is defined as its moisture content expressed as a percentage of a saturated air mixture at the same dry bulb temperature. Notice that the 100% relative humidity curve coincides with the saturation line. For example, a mixture at 75-degree dry bulb and 50% relative humidity has a humidity ratio of 65 grains. A saturated mixture at the same 75-degree dry bulb temperature can hold twice as much moisture, or 130 grains. The relative humidity of the mixture changes upon a change in the mixture's dry bulb temperature, even though its humidity ratio or absolute moisture content may not change. This is because the mixture's moisture retention capacity increases with its dry bulb temperature. Raising the dry bulb temperature from 75 to 90 degrees while maintaining a constant relative humidity of 50% will increase its humidity ratio by 42 grains. Although it's often referenced, relative humidity doesn't really mean much in terms of most of our HVAC calculations. The psychrometric chart can also quantify the enthalpy of the air mixture. Enthalpy is the total heat energy stored within the mixture expressed in BTUs per pound mass. It's affected by changes in the mixture's dry bulb temperature and/or moisture content. Finally, the specific volume of a mixture expresses the volume in cubic feet that 1 pound mass occupies when at sea level barometric pressure. A mixture's density is the inverse of its specific volume. When a mixture's dry bulb temperature is increased, it expands, and thus its specific volume increases, while its density is reduced. Also note that the specific volume, enthalpy, and humidity ratio all reference the mass of the mixture. Note that ASHRAE defines standard air density as that at sea level, 69 degrees Fahrenheit, and 0 relative humidity. This corresponds to a density of 0.075 pounds mass per cubic foot. The specific volume or density of the mixture is then used to convert between the volume flow rate and mass flow rate in our energy calculations that will follow. Now, let's begin to analyze the processes that occur in an HVAC system, starting with the zone level or the room level itself. HVAC systems are designed to provide a comfortable and healthy environment for the occupants of the spaces they serve. To do so, they're designed to maintain space temperature and humidity levels and are therefore tasked with compensating for any heat or moisture transfers that are related to processes and activities within the space. Space-sensible heat gains may originate from a number of sources, notably the space lighting, electrical equipment, and occupants, as well as any external heat gains or losses. All of these sensible heat gains affect the space dry bulb temperature and thus its sensible cooling and heating load. The most basic HVAC processes are sensible heating or cooling. These processes add or remove heat from the air without affecting the mixture's absolute moisture content. For example, a sensible cooling process occurs when an air mixture's dry bulb temperature is reduced without reaching the saturation line, thus maintaining its moisture content constant. Note that a sensible cooling process lowers the mixture's wet bulb temperature, specific volume, and enthalpy, while its relative humidity and density increase. Conversely, a sensible heating process involves an increase in the mixture's dry bulb temperature with no change in its moisture content. The mixture's wet bulb temperature, specific volume, and enthalpy will increase, while its relative humidity and density are reduced. There are also a number of latent heat contributors within an occupied space. Infiltration through the building exterior walls and windows typically involves moisture transfer, and as such affects the space latent cooling loads. In addition to being a sensible heat contributor, people add moisture to the space by means of respiration and perspiration. And finally, devices such as coffee makers may add moisture as well as heat via evaporation of water into the room air. The HVAC system must thus deliver drier supply air at a sufficient flow rate and moisture content to offset these space moisture gains. Latent cooling or heating is a process where the mixture's absolute moisture content changes while its dry bulb temperature remains the same. In theory, such a process would be modeled as a vertical line on the psychrometric chart, but in reality would only apply to cases where the moist air mixture experiences a phase change and is beyond the scope of our psychrometric chart. Instead, HVAC latent processes are most often accompanied by a change in dry bulb temperature. We'll thus refer to this as a cooling and dehumidifying process, whereby lowering the mixture's dry bulb temperature also results in a reduction in its moisture content. For example, the process of cooling outdoor air from 95-degree dry bulb and 73-degree wet bulb to a temperature of 51 degrees can be illustrated on our psychrometric chart. The mixture initially undergoes a sensible cooling process until it reaches its saturation line, which is around 64 degrees. Note that the dry bulb, wet bulb, and dew point temperatures are all the same at this point. As the mixture experiences further cooling, moisture begins to fall out, and any further temperature drop is accompanied by additional condensation. This is because the mixture's capacity to hold moisture is reduced as its dry bulb temperature is lowered. Often, a diagonal line is used to illustrate this cooling and dehumidification process. The process results in a reduction of all the mixture's properties except relative humidity and density, which is the inverse of its specific volume. Here are some equations that are commonly used in HVAC calculations. Keep in mind, these equations are all based on standard air, which has a density of 0.075 pounds mass per cubic foot. As the applicable altitude increases, the density of the air is reduced, and the HVAC equations presented on the previous slide must be corrected for the change in actual density. It can then be applied to correct volume airflow rates to perform the required sensible, latent, and total cooling for the altitude where the system is designed to operate. As you can see, the altitude correction factor is significant in high altitude locations like Denver, Colorado, whose altitude is 5,285 feet, or Tucson, Arizona. For lower altitudes like Atlanta or coastal areas like Los Angeles, correction for altitude is usually not nearly so important. Now let's take a look at the psychrometric processes that occur in a conventional mixing type air handling unit, supplying an all-air VAV system. A predetermined amount of outdoor air is drawn into the unit, filtered, and then passed through an energy recovery device such as a rotary heat wheel. Meanwhile, an equal amount of air returned from the space passes through the opposite side of the wheel. Let's look closer at what happens within the energy wheel. The wheel's membranes are coated with some type of desiccant media like alumina or molecular sieves. These are referred to as hygroscopic coatings. The coatings have inherent properties that allow them to transfer both sensible heat and moisture from one airstream to the other. Supply air passes through one sector of the wheel, while the exhaust air passes through the other sector. The mass flow rate of each airstream remains constant through the process. As the wheel rotates, both heat and moisture is transferred from the warm outdoor air to the exhaust air. The pink and blue arrows depict the outdoor airstream properties changes that occur during this process. Now, let's calculate the psychrometric effects for a real application. We'll assume that the energy wheel has a sensible efficiency of 70% and a total efficiency of 57%. First, we calculate the maximum sensible and total heat transfer that might occur if our heat transfer processes were 100% efficient. We then apply the wheel efficiencies to estimate the actual sensible and total heat transfer. We can now establish the dry bulb temperature and enthalpy of the outdoor air leaving the energy wheel, which then allows us to use the psychrometric chart to determine the other leaving airstream properties. Now let's plot the process on the psych chart. The return and outdoor air temperatures entering the wheel are identified by the symbols shown. The process can then be depicted on the psych chart as the diagonal line associated with the label 1. The diagonal direction of the process line indicates that both the sensible heat and moisture are being removed from the outdoor air as it passes through the rotating wheel. Conditions leaving the wheel now correspond to 81.6 degree dry bulb and 68.3 degree wet bulb. The next process that occurs within the air handling unit involves mixing the leaving outdoor air with the remaining return air. After passing through the energy wheel, the outdoor airstream is mixed with this return air. The psychrometric properties of the return air differ from those of the outside air, and thus the resultant mixture has its own discrete properties. For this calculation, let's assume the mass of the return air within the mixture will be 4 times that of the outdoor air when the air handling unit is operating as its designed sensible airflow rate. The dry bulb temperature and enthalpy of the mixed airstream can then be calculated using mass flow rate mixing equations. Knowing these two properties, the other properties of the air mixture can be determined. Again, the pink and blue arrows indicate increases and decreases respectively in each of the outdoor air parameters following the mixing process. Now let's plot the effect of mixing on our psych chart. Excuse me. This process is depicted as the diagonal line associated with the label 2. Conditions after the mixing occurs are accordingly determined to be 76.3 degree dry bulb and 63.8 degree wet bulb. Once the outdoor and return air have been mixed, they enter the cooling and dehumidifying coil. Here the mixture is cooled to its designed discharge air temperature, which will be responsible for providing the required sensible and latent cooling to the spaces the air handling unit serves. As the air passes through the coil, its dry bulb temperature is reduced. When the mixture's dry bulb temperature drops below its dew point temperature, moisture begins to be removed in the form of condensate. For this example, we'll assume our air mixture is cooled to saturation at 51 degrees Fahrenheit, which means both its wet bulb temperature and dew point are also 51 degrees. Again, the psych chart can be used to determine the other parameters of the saturated leaving airstream. While the mixture's mass flow rate remains constant, its volumetric flow rate becomes less because its density increases. Now let's plot the cooling and dehumidifying process on our psych chart. The initial sensible cooling process, labeled as line 3, involves cooling the mixture to its dew point temperature of 56.5 degrees Fahrenheit. Subsequent cooling to saturation at 51 degrees then lowers the mixture's moisture content from 68 grains to around 56 grains. Finally, some heat is transferred to the supply air between the time it leaves the coil and reaches the room itself. In the case of a draw-through air handling unit, the supply fan motor typically adds a degree or so of heat before the air leaves the air handling unit. Another 2 to 3 degree temperature rise can be expected as the air passes through the ductwork en route to the space. We can plot this temperature rise as a sensible heat process on the psychrometric chart, where the dry bulb temperature rises while the mixture's moisture content remains constant. Now let's take a look at a DOAS air handling unit. DOAS air handling units are designed to provide 100% outside air to the space. As such, they do not mix return and outdoor air during normal operation. Instead, the outdoor air leaving the energy wheel passes directly to the cooling and dehumidifying coil without mixing. Let's examine the psychrometric processes of a DOAS type air handling unit, starting with the energy wheel. As we're passing an equal amount of outdoor and exhaust air through the energy wheel, our leaving conditions will remain the same as that with the mixing type air handling unit. Those conditions leaving the wheel are again 81 degree dry bulb and 68 degree wet bulb. Since DOAS air handling units don't mix return and outside air, the outside air volume then passes directly into the unit's cooling coil, where it is cooled and in most cases dehumidified. Now let's look at the cooling and dehumidifying process within a DOAS air handling unit. As we've eliminated mixing with return air, the airstream conditions entering the cooling and dehumidifying coil are identical to those leaving the total energy wheel. Upon entering the coil, the air is first cooled to its dew point temperature. Subsequent cooling reduces the dry bulb temperature and moisture content until we reach our desired saturated air leaving conditions at 51 degrees Fahrenheit. The use of DOAS in hot and humid climates can result in significant energy penalties when outdoor air is at or near design conditions. The coil entering air characteristics shown on this slide represent those that occurred with our mixing type air handling unit. The energy required to obtain the leaving air conditions can be calculated using this equation, where the total cooling is equal to the mass flow rate through the coil times the mixture's enthalpy change. In the case of the mixing type air handling unit, this equates to about 324 MBH. When no mixing is performed, as in the DOAS air handling unit, the coil entering conditions are those associated with the outdoor air leaving the energy wheel. The cooling energy required to condition an equivalent mass flow rate of air would be more than 50% greater than that associated with the mixing type air handling unit. As such, DOAS air handling units are commonly paired with zone terminal units that supplement the zone cooling demands. Air-water system terminal units are fitted with integral chilled water coils that perform most of the zone sensible cooling. These coils utilize chilled water delivered above the ambient air dew point and thus do not produce condensation nor contribute to the zone's latent cooling. The sensible cooling provided by these devices allow ducted airflow rates to be reduced to that which is required for zone latent cooling. And this may result in reductions in that airflow rate of as much as 2/3 versus the mixed air or all air type system. Finally, the air leaving the coil is subjected to sensible heat gains while passing through the fan motor and downstream ductwork, as we saw before. DOAS air handling units that are intended to serve spaces with low sensible heat gain ratios such as classrooms or auditoriums, may be fitted with a secondary dehumidification device, such as the passive desiccant wheels shown here. Passive desiccant wheels utilize a similar coating as those used on the total energy wheels we previously discussed. They're specifically designed to remove additional moisture from the airstream after it has left the cooling and dehumidification coil. Supply air passes through one sector of the wheel, while return air passes through the other side. As the wheel rotates, moisture is transferred from the supply air to the warmer exhaust air passing through the other sector. At the same time, sensible heat is transferred into the supply air stream. During winter conditions, these transfers are reversed. The psychrometric process in a DOAS air handling unit with a secondary desiccant wheel are detailed in this chart. Conditioned air leaving the cooling and dehumidifying the coil enters the desiccant wheel. Moisture from the conditioned airstream is transferred to the return air. In turn, heat transfer from the return air raises the dry bulb temperature of the conditioned air while lowering its relative humidity to a level comparable to that of the return air entering the wheel. The process line that results is largely parallel to the enthalpy lines on the site chart, although there is a slight increase in the leaving air enthalpy since the process is not 100% efficient. Okay, I'm going to turn it back to Tracy.